My name is Erin Bachynski-Polić, and I'm working at the Department of Marine Technology at NTNU. And I wanted to talk today about a bit of what we've been working on recently related to wind and aerodynamic loads, specifically for floating wind turbines. So what is it that's special about a floating wind turbine? And I want to get into both time and frequency domain models. As I practiced this on the train yesterday, I had to cut quite a lot, so the second part might be quite brief. Just a little bit about myself. You maybe can hear, I originally come from the US. I studied at the University of Michigan before going to Norway to do a PhD. And then I have ended up staying in Norway since then, working at Sintef Ocean for a couple of years, and then back at the Department of Marine Technology. And I've been lucky enough to get to work both a bit experimentally and a bit numerically on dynamics of floating wind turbines. NTNU, the Norwegian University of Science and Technology, is actually the biggest university in Norway. And as you can guess from the name, it has a profile in science and technology. The Department of Marine Technology is, of course, then quite specialized in areas that are related to the marine, let's say, man-made systems in the marine environment. Historically, shipping, aquaculture, oil and gas. Increasingly, there's more being done on both subsea robots, ocean environment modeling, and floating wind. In the background, you can see this picture. I'm not sure why they put a picture of our department in the dark in the presentation that I got from a colleague. That's a temporary location where we are right now. So maybe it's because we want you to think more of the sunny days ahead when we're going to move next year to the newly built Norwegian Ocean Technology Center. And most of the center will be at T-Holt, which is where we were before. But if you come back in a year, then you'll get to see us in new and improved facilities, with new basin facilities, new teaching facilities. And on top of what you can see here, there will also be a fair amount of development in other locations. So some of our labs have been moved a bit off-site, as well as some infrastructure around the fjord and around full-scale testing that will also be part of the center. As I said, I have too much in my talk, so I'm going to skip the rest of any introduction and try to get more into the wind from there. At the department, we do quite a lot of work on floating wind turbines. So IMT, Institute for Marine Technique, is the Department of Marine Technology. FWT, floating wind turbine. That one you might see a bit more often throughout the presentation. A floating wind turbine is a complicated system, and as I guess many know, it's still a new industry, and one of the biggest challenges is to reduce costs. So what can we do in that direction? I guess that our research is sort of divided up into partly going into reducing uncertainty, in particular in loads and responses. And that means going really into higher fidelity models, better understanding, experiments, to some extent some data-driven models. And when I talk about loads and responses, that could be in many different components of the whole system. It could also be at different stages of life. And in this aspect of our research, we're maybe trying to investigate novel phenomena. And that will be somewhat what I'm trying to discuss in the first part with what we're looking at with time domain models of the wind and trying to understand what's going on with floating wind turbines. We also have an interest in looking at low fidelity approaches as well, because they have a complementary use in terms of rapid analysis of many designs. If you're wanting to try to do optimization, it's also useful to look at the low fidelity approaches. And that I wanted to represent with a little bit on the frequency domain models, which I'll get to afterwards. There's, of course, lots of other work, and I think if I had a third category, I would call it enabling efficient operations and maintenance, and that there's a lot of work, and I am not necessarily the expert to tell you about it. So what is it that makes it so interesting to look at wind loads for floating wind turbines? If we think about dynamics, we realize that we have to place natural frequencies somewhere. Okay? When I'm doing my design, I have to make a choice of where am I going to allow my system to have a resonance. If we design a floating system, we can already sort of decide that unless you're making wave energy converter, you probably don't want resonance to where the waves have the most energy. So if we look at what's a frequency spectrum shown here, on the x-axis I have frequency, in black we have the wave spectrum. All right, I don't want to be there. Okay, now I can either go below or I can go above. To go above is generally going to require more steel or more material. and it led to a more expensive structure, so I'm not really going to want to go there. You'd also see that I have these two, a blue and a green box. Those represent the turbine frequencies that are important. So the frequency of a one piece, a one rotation, or the frequency when each blade passes. So anyways, there are a lot of places I don't want to be. So I'm going to end up often placing at least some of my natural frequencies below the wave frequencies. And what we see immediately then is that the wind spectrum that's illustrated is going to be able to excite them. Which means that particularly for floating wind turbines, we now suddenly have the possibility of the wind exciting resonance, which wasn't the case for bottom fixed turbine to any great extent. Bottom fixed resonances are all higher in general than the waves. So, okay, I want to understand what's going on with the wind. Sorry. To introduce the rest of the talk, the questions that I hope that we end up answering. One is, what is special about floating wind turbine responses to the wind field models we use today? What is special about those responses when we consider wakes? And what can we do in the simple models? So, okay, I want to describe the wind because I want to do a dynamic analysis of my turbine. That means that in a way, I want to be able to build a box like this of wind. So a big box, many different points. At each point, I want to know the wind speed in 3 components, and then I'm going to use that in my analysis. What do I need to describe? Well, I need to describe the mean variation of the wind. So what we see in the mean is that there's this vertical shear. Right? The surface of the Earth or the surface of the sea acts like a boundary. So we have a boundary layer flow, increasing wind speeds upwards. So my model needs to include that. My model also needs to include, at each point, a representation of how the wind speed varies in time. And we usually think of that as, okay, I need it to include the correct frequency content. So if you've worked with waves, and you know what about a wave spectrum, similarly, I could measure the wind with 1 anemometer, and I would get a time history. I could look at the spectrum. I want to make a field that represents that. The extra complication here is that if I have 2 anemometers, I also want to know how the wind is related between those 2. And that's what's called spatial coherence. Why this starts to get interesting for floating wind turbines and for large rotors in general is that the way that the wind varies over the rotor can have a big effect on the resulting motions and loads. So for example, I like this illustration. It's trying to illustrate different types of coherence that we could have. If we take the simple one first, this case C, that would be like the wind is sort of the same over the whole rotor. And if you think like a floating wind turbine, that means, okay, now I'm going to have the same wind everywhere. That's probably going to result in large motions in the surge and pitch directions. If I have completely incoherent wind, it probably won't result in very large loads at all. Maybe that would be nice. In the other 2 cases, you see that I have a potential of certain models of coherence that give me a large yaw, and others that could give me locally a very large pitching moment. And what's interesting is that the different models that we use, the commonly used models, they give different results for the coherence. And in turn, they give different results for the responses that we see. To introduce a few names of engineering models, just so we have them in the back of our heads, I'm going to use a very simplified call chi-mol to be the model which is built up of the chi-mol spectrum and exponential coherence. The tool you might use to generate that could be TurbSim. MAN to refer to a model that's called the MAN turbulence model, which could be used in the IAC turbulence generator. And if you don't know these models, it doesn't really matter so much to know about the details, other than to say that if you look in design standards, you'll find both. So they're equally allowed, let's say, in design. If you look in design standards, they'll tell you what inputs to give for neutral conditions. I'll get back to what I mean by that. Or you can tune them. And in either case, you're going to get this box, right, that we need. If we go to a little bit higher fidelity, we could talk about large eddy simulations. At present, it's not really widely used in design, but I'll be mentioning them in the presentation as a comparison possibility. And it was nice that Emmanuel had his talk first, so you've already had a brief introduction to blade element momentum theory. Once we have this wind field, I'm going to skip the whole steps of getting the loads, but that would be done using, for example, blade element momentum. So back to this neutral conditions. Neutral is a reference to what's called atmospheric stability. And again, due to the fact that we don't have a full semester of courses to discuss the topic, I'm not going to in any detail, other than to say that it's a property of the atmosphere. You could measure it if you had the right met-mast equipment, and people have. And once they do certain measurements, you can classify the stability of the atmosphere between very stable to neutral to very unstable. This is just one example of measurements that have been seen. So for two sites, what you have on each graph on the x-axis, that is the wind speed. So for different wind speeds, you see divided up into colors from 0 to 100%, how often the atmosphere was characterized by being very unstable or very stable, or where in between. The site on the left is an onshore site. The site on the right is an offshore site. So green and sort of the light colors, those are neutral. That's what our design standards account for. A lot of the time onshore, that's true. A lot of the time offshore, that is not true. We actually see a dominance of unstable conditions, which is why it starts becoming interesting thinking about these large offshore turbines to start questioning some of these models as well. Okay, our first question though was, how do the different wind fields models affect floating wind turbine motions? And I've put a graph here, which if you have really good eyesight and want to focus on it, you can feel free. It's a little bit complicated. The top shows standard deviations of different motions, so surge, pitch, and yaw. The bottom shows the spectra of those motions for a semi-submersible where we generated the wind fields in many different ways, being using different models, Kaimal, MAN, TimeSR, I'm not going to discuss too much, and LES simulations, and different atmospheric stability conditions. So, okay, if you want, you can focus on the graph. Otherwise, I can give you the highlights, and these highlights are sort of from many different studies. One is that if you use the Kaimal model and the MAN model according to the design standard, you will, for any floating wind turbine that we've looked at, you will see that the Kaimal model will give you larger surge and pitch motions. The MAN model will give you larger yaw motions. Again, you can relate this back to how they model coherence, what we've said before. But then you might ask, okay, but which one is correct? And this is very disappointing because I don't have a good answer there. If you compare it to LES, Kaimal predicts pretty similar surge and pitch, but underpredicts the yaw. The MAN model underpredicts the surge and pitch, but provides a pretty good estimate of the yaw. So I don't know, depending on which one is more critical for your design, perhaps you could answer which one is better, but neither is perfect in any case. The reasoning behind why we see this type of behavior is that we have differences in turbulence intensity and coherence related to atmospheric stability, and we don't necessarily have enough measurements to really have great models for either of this. In general, you can be aware, though, that there's a larger turbulence intensity in unstable conditions, and that's why you'll see in general on those top graphs, for example, that the standard deviations of motions are always larger for the red points for the unstable ones. So that's at least consistent. We also tend to see higher coherence in those conditions. Yes. This was okay for the turbine that was all by itself, right? So far, we've talked about the wind models as though I put my turbine in this spot where there's just wind coming in, nothing else affecting it. The reality, however, is that turbines are going to tend to be placed in parks. So what is the effect of having another turbine in front of you? There are a couple of things. One, I'm going to call the wake deficit. So here I have turbine number one placed first. It's, of course, taking energy out of the wind. The wind is getting slowed down, just like Emmanuel talked about. And then the turbine that's behind is going to see less wind. How much less? Well, it depends how far back it is. Depends on things like atmospheric stability and what type of recovery we get. But in any case, there's going to be some mean reduction in the wind speed. And unfortunately, it's not quite so simple as to say that that moves just straight back from the turbine and we know exactly where it is all the time. The reality is that that deficit in the wind is also something that moves horizontally, it moves vertically. There's also a bit of added turbulence as well. And this effect of it moving, we're going to call wake meandering. So the reason that this, again, this is true in onshore farms, offshore farms, bottom fixed, everywhere. Why is it particularly interesting for floating? Again, these oscillations in that wake, they happen at low frequencies where we can have resonance in our floating platform. So again, we have a possibility of interesting dynamics. Another reason that it's interesting to look at a floating wind turbine with the wake deficit is that floating wind turbines do something that bottom fixed turbines don't, right? They have a mean pitch angle. The bottom fixed turbine might have a tilt that we also have in the floating one. And then in addition to that, we have this pitch. And because of that, we actually see that the wake is going to deflect vertically. We can see this in this first picture. I don't know how well you can see the turbines, but there's a first turbine. We're looking at it from the side, here around 250 meters. And 8 diameters back, I have my second turbine. And you can see that this wake is kind of moving upwards. And that's based on how much the platform is tilting. Another way to look at that is in the pictures that are below, which are showing the wind field at this U1, so a little bit upstream of the second turbine. The black circle indicates where the rotor would be, and these colors indicate the mean wind speed compared to the mean incoming wind speed. There are different cases here for stable and unstable atmospheric conditions and different wind speeds. And we see a few things. So one is that, yes, okay, well, I have this deflection of the wake. I see that the wind speeds are slower up at the upper part of the rotor. How much slower and how much it moves depends on the wind speed and depends on the stability. So again, a lot of things in play here, which we then expect to have different effects on the floater, which is then behind. We also can say a few general things about the effect of atmospheric stability on wakes, which is in stable conditions, that's illustrated at the top figure. Again, from the side, you see our 2 turbines pasted in very professional artwork way here over the wind field. We have less, let's say, smaller structures in the wind, and that's going to lead to our wake lasting longer. As we get more turbulent, bigger structures in the wind, those are going to help the wake actually recover earlier, but they're going to make it move more. So, okay, what does this mean for the turbine that's behind? That's our question 2, if you're still following along with me. And again, I've taken and put a graph for those with really good eyesight and a keen interest in looking at the numbers. I'll also provide this slide so you can get links to read the actual paper. What this is looking at is standard deviation, mean and standard deviation of different motions. So in the first row, pitch, on the second row, yaw. For the 2 turbines, the upstream and the downstream, T1 and T2, in different atmospheric stability conditions. And again, I invite you, of course, to read the paper, but we'll try to point out a few things. One is that if we look at mean values, so mean value of the pitch angle, it's going to be very dependent on the wake deficit. For this turbine, the rated wind speed is 10.6 meters per second. And that means that when we're at lower wind speeds, okay, the second turbine sees an even lower wind speed. So it has an even lower thrust. So, okay, it has an even lower mean pitch. Right above rated, the second turbine sees a slightly lower wind speed. That moves it back towards rated. So, okay, it has a larger pitch. So it's not always that things are less for turbine 2, right? Because there's also behavior of the turbine there. Standard deviation of the pitch depends a lot on the incoming turbulence and the meandering, but it can also get a little bit erased by the effects of the controller. In terms of mean yaw, you can see the mean of these different triangles and stars. That depends on what I've put as shear with quotation marks around. Because shear is really what we think of being the incoming part. But now we have a turbine which is in the wake. If you remember that figure with those circles, you could sometimes have a lower wind speed at the top and higher at the middle or the bottom, which is sort of like an inverse shear, one that we're not used to. And that ends up resulting in a different yaw angle for turbine 2, which again can have effects at the park level. And the standard deviation of the yaw has a lot to do with how the coherence is modeled, but also how the wake meandering is, because the wake moving side to side over the rotor also gives a lot of yaw. I'm a little bit unsure about my timing right now. I don't know if someone's keeping time. I did want to say a little bit about simpler models. So now we're taking a hard right turn, moving from the field of wind fields to the field of modeling the aerodynamics in frequency domain. And again, this is interesting because we want to have fast or quick models. I should avoid using fast with the context of NREL's code. We want to have quick models that we can use in optimization. Go forward one slide first. And how many people are familiar with modeling a system in frequency domain? So we have an equation here that a few people are used to working with. It's basically an equation of motion, but rewritten in terms of frequency domain. So if you think of a mass spring system, you're used to maybe then m times acceleration plus damping coefficient times a velocity plus the stiffness times a displacement is equal to a force. Very often in hydrodynamics, we would write the equation in this manner, where we move it into frequency domain by assuming that the forcing is harmonic. If we're used to hydrodynamics, we're used to all the blue terms. And now what I would like to do is introduce the red terms to represent the turbine in that equation of motion. And when I talk about system identification approaches, that means I have different ways of trying to find these A, B, and F. And I'm specifically looking at the cases where I only model the motions or structural deformations of, let's say, the floater and tower, but I don't have any degrees of freedom there for the rotation itself of the rotor. How could we identify these? Well, if we go back to the previous slide, see if I can manage that. Then we have identified and tried to classify a number of different ways. I'm just going to give a few examples. So if we go into system identification, we're on the left side there. First one that's mentioned is the fixed nacelle and turbulent wind. So that means I take my rotor, hold it in place in a time domain code, send in some turbulent wind. I measure the thrust force, and then I have, let's say, a time series of the wind averaged over the rotor, thrust force, and I use statistical methods like the spectrum and the cross spectrum to get out the excitation and add in mass and a damping. A different option, the second one, harmonic oscillation and steady wind. I take my rotor, I put it in constant wind, and then I move it back and forth. I look at the thrust force. If you're used to working in waves, again, you could think that you go to the lab, you take your platform, you move it up and down, and you measure the added mass and damping, essentially. Same idea here. Another thing that I can do numerically, I can take my rotor, put it on a big mass with a spring, put some steady wind, and do decay tests at different. I can keep changing that spring and mass to whatever I like, and do decay tests. And that would be another way of trying to measure the effect of the aerodynamics on mass. Add in mass, aerodynamic add in mass, and damping. And that would give me, again, a way of identifying those extra terms in the equation. Since we have different backgrounds, I'm going to sort of skip a little bit. The main other alternative that we consider here would be within linearization methods, what's called an analytical formulation. And again, we're not going to go through every step here, but the contrasting approach would be really to try to take your equations and step-by-step linearize them, including not only the effects of the aerodynamics, but also the effects of the inertia of the rotor and the control system as well. So let's jump to try to answer the third question, was, does this work? How can we do this, and how well does it work? If we look at the bottom graph, this is just one of many examples. This is the case for a 15 megawatt semi-submersible. Looking as a function of wind speed at the standard deviation in surge on the left, pitch on the right. The cloud and the black line, those are sort of our target. So that's what I would get with a full model, actually with an open fast model in time domain. And then all the other different colored curves are using different ways of finding those coefficients that I mentioned just before. So the goal is for the colored curve to match the black curve, right? It's the very short version. And what we found for different rotor sizes and different platforms is that this approach with the decay test and the fixed rotor seems to give the best agreement for surge and pitch motions. The other methods can work well for certain cases. And I mention this in particular because there's other research that has looked at those other methods using smaller turbines, particularly 5 megawatt, which has a simpler controller. And you can get away with a lot of things, and the controller is really simple. As we make a more complicated control, we see that the frequency domain methods more easily fail, including the analytical expressions. That's also a point that I wanted to make here, that you have a couple of different yellow curves. I see they're really hard to see on that screen. And one of them is an unmodified and a modified analytical method. And so we did have to do quite a lot of work to try to improve the analytical expressions. And you can get somewhere, but still not really all the way there yet. So again, what have we talked about today? A little bit about the describing of the wind field and why it's important for floating wind turbines. Tried to give you an idea of where we are in understanding how the different models work at present. But if I had a main message at the end, it's that there's still a lot of work needed. And really, if you've got some LiDAR measurements far offshore, I really want to know. And we're also still trying to find better ways in the frequency domain. So thanks, and a lot of credit to other people who made a number of the slides that I picked along the way.
Thank you very much. Any questions? That yes.
So I actually can't take any responsibility for the LAS that's done. So that's usually we've been working with collaborators, particularly at Berkeley, who have run most of them. In the LAS models for the wind, it's actually often more, let's say, a temperature profile, pressure profile in a really big domain that are given as the boundary conditions.
Okay.
And then you have progressively smaller domains to get a field that, yeah. So it's actually also quite hard for an LAS to directly compare to these engineering models because they have different inputs. Right?
Yes.
Yeah.
Okay.
What do you think was up with the analytical models for the frequency domain? Do you think your guess is it's a controller?
Yeah.
What was happening?
So if we get a little bit more into floaters, or actually into wind turbines in general, the controller can do two things. It can change the blade pitch angle, and it can change the generator torque. At least there's also a yaw controller, but those are the two that are active when we're looking at them. Most of the controllers that we're using have to compensate in some way for the turbine to be moving. So in particular, that term has to be included. In the analytical expressions, we're seeing that with the analytical expression, you might end up with a mean operational point, which didn't exactly match the actual mean operational point in time domain. So matching those, and then actually the next step that I think would solve things even more would be to include the rotor as a degree of freedom explicitly in the model, rather than trying to eliminate it from the model, because then you can use that change in operational point to your advantage to be more correct. If that was sufficient, yeah.
One more question by side. So
yeah.
you study mostly semi-sub, right? Floaters for your.
All the examples I showed here were semi-submersibles.
Okay. What would that change to have a TLP? Like to wake deflation, because from my understanding, when you have TLP, it is pitching upward, right, a bit. So,
well, you can make a TLP pitch upwind. Okay. I guess you can make a weird mooring system for any of the others, or a weird ballast system to make it also tilt upwind. And so if you did that instead of going upwards, you would end up with the wake going downwards. And there are a number of people who are saying that that would actually be a better solution. It looks nice when that first wake goes up above the other turbine. That seems really promising. The issue is that once you get to row 3 and 4 and 5, you start getting a really big blockage from the wind farm, and you don't get, let's say, very colloquially, new air coming in. And so it would be better to send the wake down to the seabed. So I actually think that anything that can tilt upwind could have a wind farm level advantage. Maybe not with 2 rows, but once you get to.